Good afternoon, everybody. Welcome to another, and around here it's still sunny, I don't know for how long, Wednesday afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. Now, I have to apologize due to technical difficulties, which I have fixed. I was not able to post a video for Monday's lecture. However, previous YouTube videos covered that material, and I sent out a email with links to those videos so you could see what you missed on Monday. The problem's fixed. I'm checking. Yep, I can see it's fixed. And let's continue. All right. After Monday's lecture, I realized, oops, I forgot to talk about something. So I'm going to do that right now. Now, a number of years ago, I think probably one of the worst jobs I hate to do in my house is clean the bathtub. I mean, I hate it with a passion. And you're scrubbing, and because I hated it, I let it go too long, which made it even worse. And I'm thinking and saying, wait a second, you're an organic chemist. Find a way, you should be able to find a way to clean your bathtub quickly. And I did. Now, what are you cleaning mainly out of the bathtub? Well, some dirt, but the thing that causes the most difficulty is bathtub scum. And as I talked about last week, and I think also on Monday, how do you get your hands clean or anything else? Use soap. And soap, bar soap, this will not be on a test, but it's something to help you out, where this is R sub T, which is tallow, a mixture of R sub O and R sub S, oleal and sterile, which means it's long. Now, in your water, you have calcium ions if you live in the Chicagoland area, which I do. And what happens is, and we did this in the lab, but you get this ion exchange reaction. Now, this is twice as heavy as the sodium tallowate, your bar soap. And because of that, it's no longer water soluble. And guess what? It precipitates out on your bathtub wall. And that's the stuff that's really difficult to scrub off. And I'm thinking, well, how do you break that down? Well, acid will do it. Well, you don't want to bring acid home, or vinegar, which has acetic acid, is too weak. So I'm thinking, and all of a sudden, a product I use came to mind. And afterward, guess what? It's not hard to clean my bathtub. Now, instead of 20, 30, 40 minutes of scrubbing, it's about 3 minutes. So let me teach you what this is. There's a great product out called Barkeeper's Friend. And it comes in this can. They also have a paste and a spray, but buy this can, and some powder in there. And this helps you clean up your bathtub real quick. How do you do that? Well, here's what I do. In my bathtub upstairs bathroom, the shower I don't use downstairs that often, but I do the same. Both of them have the shower heads that are removable. And I take that and turn on hot water and spray down the walls around the bathtub and also the bathtub walls with hot water. Then you take the Barkeeper's Friend and sprinkle it on there. And with a wet paper towel. Don't use sponges because they get fouled up. A good strong paper towel that's wet. Rub it just a little to make a paste, and then wait about 10 minutes. And after that, come back and either with a good paper towel or those green scrubbing, if it's real bad, you wet it and you scrub it a little. It takes like zip, zip, zip that long to get rid of the really tough stuff, where before you'd be going like this and all this, and that take forever. Then after you do that, take the shower head. If you don't have a shower head, you can use a small bucket of water and just rinse it all down. And it's done. What used to take a half hour or longer of heavy scrubbing takes me about, 3 or 4, maybe 5 minutes of actual me scrubbing. Part of it's making its face, part of it, if it's really heavy in certain spots, doing a little scrubbing, and it's gone down the drain. How does that work? Well, what are the ingredients in Barkeeper's Friend? And I thought I had one of those. And if you look here, feldspar, which is a mild abrasive, just something that's rough. But the two things are linear sodium dodecylbenzene sulfonate. That's just a soap. And this one, oxalic acid. And let's look at the whiteboard. What is oxalic acid? And this will not ever be on a test, but it will help you clean up things. This is a structure of oxalic acid. And it's a carboxylic acid, actually 2 of them in the same molecule. So if I have bathtub scum, which are these calcium carboxylate anions of sodium tallowate originally, and I react it with oxalic acid, this is a straight acid-base reaction. You get these. Now, the tallow fatty acid here is now more water soluble than this calcium carboxylate. And this calcium oxalate is quite water soluble too. And that's how you clean your bathtub easily, and the walls too. Now, the good thing about this being with soap, the soap also helps remove this too, but it's mainly the oxalic acid. Now, I'll teach you later on, but if you ever have any pots or pans or other things that have food burned on it, and first you try and deglaze it, it's called, boil some hot water in a frying pan after you get the grease out after it's cool, and then you can scrape a lot of it off if there's stuff burned on there. But if there isn't, it doesn't come off, do the same thing. Rinse it with hot water, sprinkle some Barkeeper's Friend on it, rub it, make a paste everywhere, and let it sit for about a couple minutes. Then come back with those green 3M scrubbing pads. I cut mine into quarters because you don't need the whole thing. And just like that. And the hardest thing stuck on a pot or pan comes right off. So I thought I'd teach you that, and hopefully you'll try it out. I know students have tried it out in the past and it works for them just like it works for me. All right, a couple of things. Right after today's lab, and we'll end early today, I will be sending out the email with the password for test number 3, which is available for download on D2L. You'll have until tomorrow, 11 a.m. to take test number 3 and upload it to the assignment area of D2L. For this test, and really I should have done it the whole semester, if you need an hour and a half, take an hour and a half, as long as you don't cheat. Please don't. I'll know. I have things in the test that help me identify when people do and it works, but don't. Nobody has the semester. But anyways, and don't forget to upload it on time. I promise by this Sunday, 3 p.m., if not a lot earlier, I will have your test scores in D2L for you to look at. Also, by Sunday, 3 p.m., I will send out individual emails with each points for each question you answer on test number 3. Also, next Monday, I will go through the answers for test number 3, but I will cut them out of the video. And yep, it's recording. Everything's working fine, unlike Monday. So I got that straightened out. I will be doing that. All right, let's get back to material that will be on test number 4. Now, we're talking about chirality, and chirality means handedness. And there are 2 types of objects in our world and in chemistry and molecules. One is a chiral object, the other is an achiral object. Chiral object has a non-superimposable mirror image, and an achiral object has a superimposable mirror image. And if you remember, on Monday, I talked about the difference between your right and left hands. They're mirror images. They're mirror images, if you forget about the ring for now. And if I held my right hand up to the mirror, what would I see? This. But they're not superimposable. Now, what do I mean by superimposable? These are models of carbons. I used to do a lab in this 170, and students hated it. I mean, with a passion, so I cut it out. I mean, if students aren't having fun in the lab, it doesn't help if they're learning something if they really hate it. Now, these are carbon atoms, and here are the 4 bonds to carbon. Think of hydrogens at the end, and carbon to center. They're mirror images, but they're superimposable. If I could squeeze these together, notice this silver tube lines up here, this one, this black tube, this black rod, actually not a tube, and the center, and I could push it together. So these would be achiral models, or carbon atoms, which I'll talk about in a little while. So let's have some fun with, is this chiral or not? Oh, warning, I'm going to be doing some artwork, so be sure not to laugh too hard and crack a rib. I don't want that to happen. All right. I was telling my class this morning at COD, College of DuPage, back when I was a junior in college, on the 14th of April, we had a snowstorm and we had 14 inches of snow. Next day it got warm and all melted, so we had floods. And the reason I remember that is the next day, April 15th, is when taxes are due. That's the only time in my lifetime that in Northern Illinois, they gave an extra day or two for people to get in their taxes. By the way, good news, I'm a procrastinator when it comes to taxes. I'm getting better. I actually mailed mine in yesterday. Usually I can do it the day before or two. I really procrastinate. All right, let's take a look at this. Now, remember, chiral means it has a non-superimposable mirror image, and achiral, it has a superimposable mirror image. Now, let's look at number A, or letter A, your left winter glove. Now, as soon as you see the word right or left, you know it's going to be achiral. What am I saying? Even I make a mistake once in a while. I caught it though. It will be chiral, handedness. And if you don't believe me, take your left glove, hold it up to a mirror, and it'll be your right glove. And they're non-superimposable like your hands. The other thing which can tell is, have you ever tried putting your left winter glove on your right hand? Oh, it doesn't fit right. That's because your hands are chiral and could tell that the glove is chiral and on the wrong hand. Now, let's talk about mittens. And here I have the kind that don't have the leather palm or any kind of writing on the back. And warning, warning, Dr. White artwork. Oh, that's a better one. I've done worse. Here's your mitten, and it can be right or left hand, doesn't matter. And if I have my mirror here, wow, I'm getting better at this, is your mirror image. And if I pick this up and rotate it, you'll see it's superimposable on itself, on its mirror image. Therefore, it has a superimposable mirror image. And what does that mean? It means it's achiral. Now, let's look at a tube sock with no toes. If you're a woman, you know, you can buy the tube socks that have the toes in it. Men don't have those, at least I've never seen them. So this is one without toes. Like I said, I'm not going to be an artist ever. Let's fix it out. Yeah, that's better. And here you have the tube sock. Dr. White loves double-soled tube socks. I wear them all the time. And its mirror image would be this. And if you rotate this, you'll find it's superimposable on its mirror image. And therefore, it has a superimposable mirror image, and that would be achiral. And finally, let's do a four-door car. And the super warning, don't laugh too hard. Here's a four-door car. Here's the steering wheel, the headlights, the tailpipe, the tail lights, the wheels. And the question is this chiral or achiral? Well, let's hold it up to a mirror. And what's closest to the mirror, you'll see first in the reflection. And notice the steering wheel is closest, so it would be here. And you have a headlight right here, one over here, this, the door, this. I have my tailpipe, or actually it would be over here, and the other brake light. Now, remember the wheels on this car are on the bottom, the roof is on the top. And if I just picked it up and put it over it, it's not superimposable. Just look at the steering wheel. This is on this side. When I picked this up and just laid it over, this would be on the opposite side. Now, somebody might say, well, rotate it over. Well, this one, you rotate it, would have the wheels facing down, the roof up. This would have the roof down, the wheels up, and it wouldn't be. So a car has a non-superimposable mirror image, and that makes it chiral. Quick Dr. White story. If you notice the car on the right, my right, and has the steering wheel on the opposite side of where we normally have it. And back when I worked for two huge international companies, I would go to Manchester and Liverpool a lot in England. And Manchester, twice I almost got killed. Both times a Bobby, their policeman, saved me by grabbing me by the end and pulling me back when I was going to step and cross the street. And said, sir, you're American. Look at the street down there. And it says, look the opposite way than you're used to, or something like that. And that's because the cars on the opposite side of the road, so as opposed to American. And the steering wheel is there. And whenever I never drove in England, thank goodness, but you'd be sitting in a car in the front seat with a colleague who was from England, I would be, and we pull up to the stop sign and he sees me grabbing the wheel and putting my foot up where the brake would be, said, you're not driving. I said, it feels like it when I'm sitting on the side of the car, I should be. My mind just kicked in. Now, quick addendum to that story. How did I make sure I didn't get killed again crossing the streets in London or Manchester or Liverpool? Well, I came up with a great idea. When I was about to cross the street, hopefully there was a little old lady or man, and I'd wait until they got in the street because I figured they knew the right way to look because they were from that area. And luckily they were. So that's how I didn't get killed ever again in England crossing the street. By the way, a beautiful city near Manchester, it's called Chester, and part of the walls of Chester go back, predate the Middle Ages. In fact, part of it was actually a Roman fort. Amazing going to Europe. And here I give 4 for you to have fun with. And it's your turn to figure out, are those 4 a round white ball, plain white ball, your left shoe, a school bus, and a piece of uncooked rice? Are those chiral or achiral objects? Have fun. If you know anybody needing organic chemistry, I'll be teaching it this summer online, same as this, except instead of starting at 1, we'll start at 2. It'll be Monday, Tuesday, Wednesday, and Thursday because it's summer and it's only an 8-week course. But surprisingly, summer students do just as well, if not better, than my fall spring. That's both on Zoom and back when we were face-to-face. I think it's because it's the only class they're taking during the summer. Who knows? Remember, you're trying to find out, are these objects chiral or achiral? 3 points each. All right, looks like everybody's done, so let me get to work. All right, if you have a round ball and you look at its mirror image, it will be this, and they're superimposable. So superimposable mirror image, it's achiral. A means without handedness. Now, as soon as you see the word left or right, that's a giveaway, it's chiral. But I'm not going to draw an image, but if you take your left shoe and hold it up to a mirror, you'll see your right shoe. And if you've ever tried to put your left shoe on your right foot, it doesn't work that well. All right, now a school bus will be the same as my car up here, except it's got a bigger door and it's longer. And guess what? It's chiral. Now, one of the things I didn't talk about on the car here, if you were standing right here in front of the car and I said, get in on the left side, you would know which side to go to. Well, how do you know that? Because it's chiral. So a school bus is also chiral, has a non-superimposable mirror image. Now, piece of rice, and Dr. White loves basmati rice. I think I'm pronouncing it incorrectly, but that's my favorite type. You have a grain of rice uncooked. I don't think cooked makes a difference, but it sounded good. And here's the mirror image. And if I did it right, they're identical. And you could pick this up and superimpose that. So it has a superimposable mirror image. And therefore, it's achiral. Now, before we leave this, I'll ask you to think about one more. And I don't have it on because I'm wearing sweatpants. Don't look. But anyways, since the pandemic, I've been wearing only sweatpants. They're more comfortable. But if you have a regular pair of pants with a zipper and a button in the front and front pockets and back pockets, is that pair of pants chiral or achiral? And the answer is chiral. Think about it. In your pants, if you have the kind with the zipper in the front, with the button in the pockets, if you put your left leg in the right pant and vice versa, your right and the left, the zipper would be behind you and the pockets, and it wouldn't fit good either. And if we were face to face, I'd be wearing a pair of pants like that before the pandemic. Now, if I'm teaching, I'm still in my sweatpants. Shh, don't tell. But anyways, I told the students, think about it, if I put my pants on backwards and I come into class that way, I hope one of you at least very quickly gets me help, because there's something wrong with me if I do that. And it doesn't fit right. That's because your pants like that are chiral. And your body is chiral too. Left hand, right side, left side. Your body's chiral. All right, now this is chemistry, organic chemistry. And what do we talk about? Molecules and atoms. And in chemistry, we have what's known as a chiral center. And that's an atom in a molecule that has 4 different groups, and it's tetrahedral when we're talking about carbon bonded to it. So a chiral center has 4 different groups attached to it. And let me show you why that's true. All right, show and tell time. Everybody see this okay? And it's in color. Now, assume the center is carbon, and this shape, like this here, is called tetrahedral. Now, here I have a black rod, a silver tube, red, and yellow. Now, if I had the mirror image, think of a mirror right here. This is the mirror image of this. Notice black, black, yellow into yellow, red into red, and back here I have the silver. Now, are they superimposable? Don't know. If you notice, the black line up, the silver line up, but right here, this has red, this has yellow on this side. This has red, this has yellow. They're not superimposable. We say, Dr. White, turn it upside down. All right. And now the reds are on the same side, the yellows, but look on top here. One has black, one has silver. That's not the same. So these are mirror images. Oops, let me get it. Mirror images, but they're not superimposable. So if this were a carbon atom with 4 different things on it, it would be a chiral carbon. And it turns out having chiral carbons affects the molecule the same way your right and left hand does. And I'll talk more about it this chapter. Now, let's look at the following. and 3 points each circle the chiral carbons in the following molecules. And let's look at A. And the question is, circle the chiral carbons. Well, what's a chiral carbon? That's a carbon with 4 different groups. If it has 2 or more of the same groups or atoms on it, it can't be chiral. So if you look at this carbon right here, has 3 hydrogens, that's out. This one has 2 hydrogens. It's not 4 different groups. That's out. Same thing here. Same thing here. So those are all not chiral carbons. Now, if we look at this carbon, it has a hydrogen hydroxyl group, this methyl group, and this group I'll call R. I can call this R prime. So it has hydrogen, hydroxyl, R prime, and R, 4 different groups. So that's a chiral carbon. I actually circled more than a carbon. So let's do this. If you were to do that on a test, I would mark it wrong. There you go. Now, let's look at this carbon. It's got a hydrogen. Give me a second to do something. Actually, it took more than 1 second. It has this hydrogen, a chlorine, a methyl group I'll call R, and then all of this on this carbon I'll call R prime. Are they all different? Yes. And a chiral carbon has 4 different groups or atoms or combination. So that would be a chiral, and that's who you'd find. Now, let's do another molecule. All right. And that's the sulfur, making it a thiol. All right, let's look at this. And the question is, circle the chiral carbons. So what do? Well, the quick way, don't tell anybody I'm helping you out like this. If something has 2 or more of the same group or atoms on it, it cannot be a chiral carbon. So immediately, this is out. Now, if a carbon is in a double or triple bond, it can have 4 different groups. So this carbon and this carbon are in a double bond, they're out. And this carbon is in a double bond to oxygen, it's out. And that leaves us with 2 carbons left to go. And if we look at this carbon, I have a hydrogen, a thiol, this methyl I'll call R, and this all the way over here, all that I'll call R prime. So this carbon right here has a hydrogen, thiol, R, and R prime, 4 different groups. It's chiral. And if we look at this carbon, has a hydrogen, an iodine, this aldehyde, and this group. I'll call this R and R prime. And again, hydrogen, iodine, R, and R prime, 4 different groups or 4 different atoms or combination thereof. Therefore, that's chiral. And why don't you try this one? Wow, that's a big molecule. Circle the chiral carbons, 3 points each. All right, I think everybody's done, so I better get to work. So remember, chiral carbon, 4 different groups, 4 different atoms, or a combination of 4 different groups or atoms. If you have 2 or more of the same thing on a carbon, atom or groups, it can't be chiral. This is out. 3 hydrogens, 2 hydrogens, that's out. 2 hydrogens, that's out. If we look at this carbon, 2 methyls, 2 of the same group, that's out. If it's in a triple or double bond, these 2 carbons are out. This has 2 hydrogens, it's out. This has 3 hydrogens, it can't be. And if we look at this carbon here, it's double bond to oxygen. And if a carbon is in a double or triple bond, it's out. So we only have 2 left to go. If we look at this carbon, hydrogen, halogen, that's Br, R, and this whole thing here is different than R prime. So it's got 1, 2, 3, 4. It's chiral. And let me clean this up. If we look at this carbon, hydrogen hydroxyl group, this whole thing I'm going to call R. And this side, this whole thing, this group, I'll call R prime because it's different than R. And therefore, this has hydrogen, hydroxyl, R, and R prime. 4 different groups or 4 different atoms or a combination, in this case, 4 different groups or atoms. And that's chiral. Now, there's something I'll talk more about how it's generated. This is called the Fischer projection. And I'm writing the Fischer projection for glucose. And this is the most abundant sugar in nature. And each intersection of a line here is a carbon. And the question is, circle the chiral carbons. I'll let you try that first and I'll do it. Your turn, circle the chiral carbons. All right, I think everybody's done. Let's take a look at it. Again, circling the chiral carbons. A chiral carbon is a molecule or carbon atom that has 4 different groups, 4 different atoms, or a combination of 4 different groups or atoms. If it's in a double bond, it can't be chiral. And notice this carbon right here is in double bond to oxygen, so that's out. This has 2 hydrogens, can't have 4 different groups, it's out. Now, if we look at this carbon here, I have a hydrogen hydroxyl group, this aldehyde, and then all of this, which I'll call R. That's better. This I call R prime. So it has hydrogen hydroxyl R prime, 4 different groups. It's chiral. And if I look at this carbon, the same thing would be true, same thing here, and same thing here. So in glucose, there are 4 chiral carbons. And that's how you identify chiral carbons. And if I look at the clock, it's time to take a 5-minute break where I'm going to get up and stretch, and I'll see you in 5 minutes at 1:55. Let's get going. All right. Turns out we've caught up. So I'm going to do the lab. You're going to get out early, and you'll be able to start test number 3 once we're done. Now, I have to say right now, I'm very sad. Why am I sad? Because this is such a fun lab to do face-to-face, because students really like that. But with the pandemic and where it was, I decided, because I did have a choice to do a lab face-to-face and on Monday do a Zoom lecture. I decided, no, let's keep it all Zoom because it's safer. And with the new variant starting to get dangerous again, I think I made the right choice. All right, let's talk about today's lab. Today's lab works with polymers. As you know, polymers, poly, many units hooked together to make macro, large molecules. So let's look at today's lab. And as you see, polymers, the word coming, polymer coming, poly, many, mer, single units. And these are very large molecules with repeating units. Now, I should warn you, I have about 5 patents, US patents in polymers, so I know this area just a little, especially the first part. Now, let's talk about polyurethane polymers. Now, this is an important type of polymer called urethane polymers, and poly means many, urethane. Now, the urethane functional group, which I won't go through in class, but I'll talk about now. Remember, anything I talk about in lab will never be on a test unless I talk about in lecture. And there are many functional groups I just don't have the time to cover in a 16-week course. And I've made a decision years ago when I started teaching this, talk about the functional groups in a lecture. They're most important to my students in their daily life. Well, there are a few I had to leave out, and this is a couple of them. All right, this right here is called an isocyanate. And it's an R group on a nitrogen, which is double bond to carbon, which is double bond to oxygen. And this reacts much quicker than a carboxylic acid with an alcohol to make, this is called the urethane. A urethane is a carbonyl with an oxygen with R prime and a nitrogen with R. And this is called the urethane. And for polymers, you have more of the same, one of the same functional group in each molecule. We use a diisocyanate in making a polyurethane polymer, or as you'll see, a foam, and the alcohol is called a polyol. And a polyol, poly, many, OL alcohol, is a molecule with many alcohol functional groups. And the polymer formed from this is called a polyurethane. You have this repeating over and over again. And this reaction is very exothermic. That means it gives off heat. Now, because it's giving off heat, if you have a low boiling liquid in the reaction mixture, you can make what's called a polyurethane foam. And this foam can be rigid like bricks or flexible like your pillow. And there are 2 different types. We used to make both in the lab, and I couldn't get the chemicals anymore for the flexible. So if we were working, you would make the rigid foam. Now, what are some uses of, and you should be taking notes now, of urethane foam? It's an outstanding insulator. And how many of you have ever seen a refrigerator from the 1940s or 50s? The walls are about this thick, really thick. Now, if you look, go in your kitchen or wherever you're living in the kitchen, you'll see that between the inside box and the outside of the refrigerator, your walls are this thick. They're not that thick like the old ones. Why? Because the old ones use glass wool to insulate the cold inner box from the outside. And therefore you have thick padding to do that. Now, for many years now, instead of using that, they're using a urethane foam, which you need less thickness to get the same or better insulating properties. Now, urethane foam is also used to insulate houses, and they can spray it on or put slabs. And because the people making the foams, when they're doing it, usually maybe have a high school education, the people in the urethane foam industry came up with a really amazing concept. And that concept is using an A and B side for urethane foam formulation. And there are certain things that are measured called the cream time and tap time. So let's look at a basic urethane foam formulation. Take good notes. And you have an A side, which is this, the isocyanate. Or a polymeric isocyanate, it's sometimes called. Then the B side contains the polyol, the polyhydroxy-many-hydroxyaldehyde. It has what's called the blowing agent. And a blowing agent is a low boiling inert material, liquid or substance. It used to be Freon till they found out what Freon did to the ozone layer of our planet. Now they use other blowing agents. It has a catalyst. As I mentioned when we were going through, this is usually a tertiary amine catalyst. That's the most prevalent. And then it has a silicone surfactant. That helps make the bubbles trapped in the foam uniform. And the nice thing about having an A and B side is most of the formulations you buy from places, you put equal amounts of A and B together and mix it together. And different products have different amount of catalysts and whatever. Now, when you make a foam, you can have one that sets up quickly or slowly. And how do you measure that? That's called the cream time. And this is when the reaction starts. Now, why is it called cream time? This is my conjecture. If you look at when you're mixing it, the isocyanate for rigid foams is usually almost like black coffee, that color. The B side is very slight yellow or almost clear. When you mix them together and the reaction starts inside the cup you're doing it in, it looks like you've just poured milk into coffee or cream. You know how it gets lightens up when you pour milk or cream into coffee. Dr. White doesn't like coffee, so I'll let you use your imagination. But I've seen it with friends when we're out or at their homes. You'll see that change. And that's when the reaction starts. And this is an important parameter that you measure. Now, you can affect the cream time by adding more or less catalyst. And more catalyst makes it go quicker, less catalyst makes it go slower. Now, there's another important thing that you measure, and that's called the tap-free time. And that's when the top of the foam is no longer sticky. And if you were making it in a mold, you could take it out then. Just like if you're making cupcakes in a cupcake pan. Is that the right term for that? Or tray or whatever? Dr. White doesn't bake that well. Cook, yes. Bake, no. That's what bakeries are for. And, oh, that reminds me, time out. Before I forget, I believe this Sunday is Easter. Let me go look and check. And the answer is yes, it is. So for all of you celebrating Easter, I hope you have a happy Easter. For those who don't know, this Friday at sundown is the beginning of Passover. For all of you celebrating Passover, I hope you have a happy Passover and you get all the matzo balls you want, and they're good ones, and other good things too. And for those who don't celebrate Easter or Passover, I hope you have a nice weekend. And back to the lab. Now, in this lab, if we were to do it in a large plastic cup, and I've already told you in the hood, foot paper, we have some newspaper, and over that, some plastic wrap. It's because urethane sticks to everything. It's hard to get off. So that's why we put that down. You weigh 10 grams of the A side, the isocyanate, in a beaker, separate, or in a plastic cup. In a beaker, you weigh out approximately 10 grams of the B side, and you put it, see, I do have over the newspaper, with a tongue depressor, you pour the B side into the A side, mix, and watch. And you'll see when it turns from a light dark brown to light cream colored brown, record that time in seconds. And you'll feel the outside of the cup, if we were face to face, doesn't get hot. And then every once in a while, touch the top of the foam with your tongue depressor, see when it's no longer sticky. And you'll record that as a tap-free time. Oh, time out for commercial. All right, thumbs up, people. Everybody sees slow rise urethane foam on your screen. Thank you. Let me do this and enjoy.
3 pound per cubic foot molding foam that we want to discuss some of its attributes. This material starts its life off as thin liquids. It's going to be mixed at a 1-to-1 volume measurement, and then it's going to expand. It's going to expand to form a very lightweight foam. And as we said, in this case, it's a 3 pound per cubic foot density foam. So it's going to expand 24 times its liquid volume to create a lightweight, non-absorbing, closed-cell foam that can be easily sanded or carved to dimensional shape. It can be cast as backups or as free-standing forms. It can be painted with automotive paint and used in conjunction with fiberglass resins. In conjunction, it can be used for flotation. It has a extremely good compressive strength. This particular 3-pound foam has 40 pounds per square inch compressive strength, so it'll support a human walking on it. But also it's good down to depths of about 300 foot in the water. To demonstrate how this liquid foam is going to actually be mixed and used, we first conditioned our liquids to 72 degrees Fahrenheit. Best temperature to be at. Hotter means faster reaction. Colder means a slower reaction is going to create higher density foam than desired. We're going to measure out in equal portions in liquid. In this case, we've had some pre-marked beakers. We measure out part B, and now we're going to measure out part A.
We would use
And then we're going to
balance.
take a flat spatula, not a round dowel, and we're going to pour one into the other, and we're going to simply mix. And it's important that you quickly scrape the sides and the bottom of the container to incorporate all the A and the B.
See how it's gotten light?
Reactive. Doesn't take much. When the material starts to react, it'll form.
Everybody, see how it's gotten light here? And if I back it up, you see in the cup he's pouring, right now it's a black or dark color, and then it got light. As soon as it got light, that's the cream time.
Chiral expands. We'll pretty well got it mixed, and it's going to create just a little bit of heat on its own. Again, 72 degrees is the perfect temperature to start mixing that. It gives you about a minute or so of time to actually mix the foam and pour it into the mold. You got to be careful now not to put too much foam into a closed cavity mold, because it does create quite a bit of pressure on its own, and it could warp your mold. So now it's starting to come up. And actually, to demonstrate this, we're just going to let it come up to kind of show you what we call free rise in this. So it comes out.
Oh, it's
going to expand. And within about 2 or 3 minutes, it's going to get to be full hardness. And we'll be able to actually pick this up, carve it, and show you how it's used. It's best not to get this on your hands, and I'm not wearing gloves, but you should wear gloves with this right now, because it loves to stick to human hands.
When you do it, you
That's
would be
about it.
wearing gloves in the lab.
And you can see I only had about 500 milliliters of liquid, but you can get a sense of how much volume with this. Now, foam is sold in different densities, from very, very lightweight packaging foam, which is about 3/4 of a pound per cubic foot density, all the way up to heavy furniture foams, which can be as high as 15 to 20 pounds per cubic foot. And every time they go up in density, the carvability and the machinability goes up to it as well. You can see this is already forming a nice solid. And within a few more minutes, I'll be able to pick this up and actually carve it for you. Well, it's only been about 5 minutes since we initially mixed our foam. And you can see it's pretty well set. It doesn't stick to polyethylene or propylene plastics, so common garbage bags work quite well as a barrier. As you can see, it's durable and it's fairly lightweight. And as we mentioned earlier, it's easy to carve. The carved and sanded. The integrity of the foam gets better the more that the liquids are mixed.
All right, now, having worked in urethane foams, one of the things that's a hallmark of someone who knows their urethane foam is the following. Can you mix and formulate a urethane foam that when you pour it, you have enough catalyst that as soon as it hits the ground, it hardens? And it took me 5 tries, but this is one of my prized possessions. And yes, I made it myself. This is using some of the chemicals I invented, and it's got dust in here. Sorry about that. I made this in about 1984. Wow, this is older than most of you have been alive. Oh, I shouldn't have said that. But anyways, this is a urethane foam, and depending on the density, this is pretty hard. And that's what you would be making, not this type, but similar. All right. Now, again, cream time is when the reaction starts, it changes color. You saw that on the video. And you notice how he was able to touch it. It was no longer tack-free or sticky. Now, the ones we would make in the lab, after about an hour or so, it would be as hard as wood. I mean, really hard. And different densities, he had a softer, lower density. And because you're not going to do it in the lab, here's the data. Here's the cream time. Here's the tack-free time. And yes, there was heat given off, exotherm, and it was a solid light brown, like I just showed you. All right, let's move on. Now, another type of polymer called polyamide polymers is also known as nylon. And nylon is the reaction where you make an amide function. And here, instead of using a carboxylic acid, we use an acid chloride. This reacts the same way as a carboxylic acid, but very fast. Now, one of the things I don't have in this reaction, you also make hydrochloric acid. Now, you know, amines are bases which would react and neutralize some of your amine. So when we do this, we put in a little sodium hydroxide in here to neutralize the HCl that's made. Now, this is showing just a single acid chloride, single amine. To make a polymer, use a diacid chloride, di meaning two acid chloride, and a diamine, two amines. And the repeating unit is a polyamide, which was called nylon. Now, this stuff is really neat to do. And I'll show you the video now. And you can go back and look at this again on your own, but I like to take time just to show it to you.
If you struggle to lose weight, you must see this.
Sorry about this, but I have no
A
control.
fat dissolving loop.
Familiar mushroom cloud snakes skyward, hurling the atom's deadly radiation high into the heavens.
Okay, this is the aqueous solution. I'm going to pour this in here.
Dr. White, we can't see it.
And
Uh-oh,
that aqueous solution.
thank you. I sometimes forget to share the right screen. Can you see it now? All right, let's start again.
Okay, this is the aqueous solution. I'm going to pour this in here. And that aqueous solution contains the acid, the diacid. And this is a solution of the hexane diamine that's dissolved in hexane, and hexane is less dense than water. So this solution is going to float on top of the other one. And then where the two solutions come together, the interface between these two solutions is where this reaction is going to take place. How many fingers do I have anyway? Here we
While
go.
he's doing that, in the beaker is the diacid. In the Erlenmeyer
Okay.
flask he's
So I'm
picking up
very
now
carefully going to pour
is the
this down the
diamine.
side, and then where the interface is, we'll have contact between the diacid and the diamino hexane. And the hexane layer is floating on the top here. But of course, where they come together is where the polymer can be made, where the condensation reaction is happening. So then I'm going to reach in here, and where the interface is, I'm going to pull out some nylon. So
The white stuff is nylon.
we'll see how much nylon we can pull out of this thing. There's a meter or so. 2. There are records set for this, and so I think it's actually in the Guinness Book of Records. I'm sure we're going to beat that record today.
All right. We would normally wrap it around a beaker And let me see if I can get back to this. If you can't, it's hard to see, but right here between the two layers, you could see this white film forming. And that's because the top layer has the diamine, the bottom layer has the acid chloride, the diacid chloride. And that's where they touch, they form a reaction. And this is how you make nylon.
Sure, we're gonna beat that. 6.
And
Yeah,
you can
see that
keep
you
on
get a lot
going
of
on and
material
on for
out of
about,
a very small quantity.
in a
All
lab
the
when we do
different
it,
areas
for about
the-
5 minutes. And that's how you make nylon. Now, in the lab, and thumbs up, people, can everybody see the lab now? Hold on. Thank you, Sargon. All right, one beaker, you label A, the other B, and A, you measure out 25 milliliters of dichloromethane. Then you put in sebacol chloride, is the diacid chloride, in that beaker. In a separate beaker, B, you put in 20 milliliters of DI water, and he said he had the water in with the diacid. He was wrong there. He got confused because you never want water with the diacid chloride. It will react. But anyways, you have this amount of water with the hexane diamine, and then you add a little sodium hydroxide. And notice how he tipped the beaker with the acid chloride and carefully down the side of the beaker poured beaker B. And then one like this. Then you take a wire hook, you use tongs, and you pull up that interface, that white solid, and you wrap it around a beaker and you start rolling. And I tell students, keep on rolling until you get tired. Usually they can do it for a good 5 minutes, and it's just a lot of fun. And then dispose of it where I tell you. Now, the last one is the reaction of alcohols with boric acid, or really sodium borax, which is the same thing. It's one of the rare times you're going to see me balance an equation. And this is an alcohol. This is boric acid. And you get what's called a borate ester. And interesting enough, I have a patent in borate esters. But anyways, when you have a polyol, a molecule with a lot of hydroxyl groups, you get a polymer that cross-links really nice, and the borate ester looks like monster slime. And here, you're going to try 2 different alcohols. One is not a polyol, isopropyl alcohol, which I should put it's 2-propanol, and the other is Elmer's glue, polyvinyl alcohol. And Elmer's glue, polyvinyl alcohol, has this structure. And N is the order of about 1 million. Yes, there are a lot of hydroxyl groups in each of the polyvinyl alcohol in Elmer's glue, which is a mixture of polyvinyl alcohol and water. And when you mix together, the isopropyl alcohol with the boric acid stays clear. When you do it with the polyvinyl alcohol, how do you like that scientific description? Gooey, slimy, white solid. And it's fun to do. And you can do this at home. If you want, go to wherever you get Elmer's glue, get some, and buy some 20-multene borax, which you can get at any supermarket. You mix them together with water, you'll get the same reaction. And this one, for each alcohol, you'd mix in a dry beaker, a couple milliliters of the alcohol being tested, and then about 5 milliliters of DI water. Then you add about 5 milliliters of the boric acid and record your observation after about 5 minutes. Well, since we're not doing it in the lab, through the miracle of YouTube, I don't know if it's a miracle, but let me do this. Let me make sure I do this. Sorry about the commercial. I don't pay for commercial for YouTube. Everybody see
Hey
YouTube?
everyone. Today I'm so excited to show you our favorite slime recipe. This is the most amazing, softest, gooey, oozy slime, and it's so much fun to play with. First, we will begin by creating our slime activator. You use 1 cup of hot water with half a teaspoon of borax.
I have the solutions made
Make
up
sure to
for you
stir
in
it
the
well
lab.
so that you dissolve all the powder. Once you're done mixing, you can keep it to the side. If you prefer not to use the borax activator, you could also use contact lens solution that contains boric acid. Now we'll start our slime. I'm using 1 part of glue, so 1 bottle of Elmer's PVA glue, and I'm going to mix it with warm water. So I'm going to add the warm water into the glue bottle.
We do this in beakers.
Now I'm going to close the top and I'm going to shake it. That will help spread the leftover glue inside. Then open it up and add it to your mixture. Now just go ahead and mix it all together so that you don't end up with any clumps. You want a nice smooth mixture.
We just used a pure glue. We don't dilute it in water.
I tend to keep on hand a bunch of ice cream sticks because they're the easiest to clean up afterwards and they do a great job of mixing. Now you'll add your food color of choice. I choose to use food color gels because I like how vibrant the colors come out. You just need 1 drop. I'm going today with a purple color. For some reason it's looking a bit bluish. I chose purple because we currently have a million different slimes at home. So we've got a butter slime that's yellow, we have 2 fluffy slimes that are pink and blue. You can find the recipes and video tutorials by clicking one of the links. Keep mixing until you don't have any streaks left over. Now your borax mixture would have had time to dissolve. Make sure that you give it a good mix before you start adding it in. This is really important that you add it in really slowly because this is sort of the part that's going to make or break your slime. So I tend to go and add in a teaspoon at a time and then I mix, and then I can add another teaspoon at a time and mix. You will see that it starts to sticking together. To actually touch the borax mixture with your bare hands, unless it's already
Is that
mixed
cool or
into
is
the
that
slime.
cool? Now you know I'm a chemist. Oh, I'm
You
excited.
can add in between 5 to 7 teaspoons of borax. I probably added I think I added 6 teaspoons, and I could tell from the consistency with my hands that it was still a little bit too sticky. So I went ahead and added 1 more, mixed again, and then now you start kneading it.
And what she was kneading, that's a polymer. That's the polymer formed from polyvinyl alcohol with borax or boric acid. And this lab, when you do it with isopropyl alcohol or isopropanol, 2-propanol, you don't see that. When you do it with the Elmer's glue, you do see that. Now, I do have out, I usually don't say the students have to do it, but we put food coloring out if you want. If not, you get a gooey, slimy, white solid, which is what she had. And that's today's lab. And with that, let me remind you, in a little while, I'll be sending out the password for test number 3. You have until tomorrow, 11 a.m. to get it uploaded, your answers. If you don't have a printer, just handwrite out the answers. You don't have to write out the whole problem, and take up to an hour and a half if you want. Don't worry, just keep your eyes on your own paper. No, we're not in a classroom. But anyways, and with that, let me remind you, don't forget there's a new link that I posted, the correct one, on G2L login or the SCHEM 170. I also sent out email of my office hour tonight. If you have any questions, stop by. And also until about 9 o'clock, about every 2 hours, I'll check my email. And tomorrow morning I have to teach, but early on, I'll check. I leave by 7:30, 7:45. I'll check my email, and when I get back, I'll check if you have any problems. And with that, I'll see you on Monday. Don't forget, by Sunday, 3 p.m., I will have posted your test number 3 scores in G2L. And by Sunday, 3 p.m., I will have emailed out your individual points for each answer on test number 3. Hopefully I'll get it done Saturday. And with that, I'll see you on Monday. Don't forget, on Monday, I will go through the whole test number 3 answers, but I'll cut it out of the video. And I'll be posting later today, today's video. And with that, those of you who celebrate Easter, happy Easter. Those of you who celebrate Passover, happy Passover. Those of you who don't celebrate either of those holidays, have a happy weekend. With that, I'm done. Gang gesund. Goodbye.
Bye, thank you.
You're welcome.